Okay, good morning. All right, so first of all, our exam location has been updated. Originally, you might remember that one of the three exams was not in Elliott Hall, but now all three will be in Elliott Hall. Okay, so that's going to make it very easy for everyone here. So once again, exam 1, Thursday, September 21, 6:30 p.m., Elliott Hall. They're all on a Thursday, and they're all at 6:30 p.m., and they're all in the same place. Exam 1 is coming up in a little bit, about 2 weeks. Okay. Speaking of Elliott Hall, if you have never taken an exam in Elliott Hall, it can be a little bit intimidating. And therefore, the Academic Success Center has scheduled this practice session where you get a chance to go into Elliott Hall, take a practice exam under the exact same exam conditions, just to get you a feel of what it's like to take exam in Elliott Hall. If you're interested, that thing is on September 11, 8 p.m. Space is limited. Be sure you register at the address at the bottom of that page. All right, so once again, it's a 60-minute timed practice exam. They'll take an old exam and for you to take it with the Scantron and all that good stuff and put you under exactly the same set of conditions you will be under when you take the real exam, just to give you a feel and kind of a dress rehearsal for the real thing. Okay? So, once again, if you want to take advantage of that, please register online. And I'll put that flyer on the other projector here, so if you didn't get a chance to write it down, here it is. Let me focus that a little bit. Okay. And today we'll look at section 2.5. We're going to cover an important concept in calculus called continuity. If you take a function, we say that the function is continuous at x is equal to some number a, if the graph of that function at x is equal to a has no breaks. That's when we say a function is continuous at x is equal to whatever that number a is. And a good way to get a better feel of that is if you are tracing the graph by hand. You shouldn't have to lift your hand off the paper or whatever you're drawing on at x is equal to a. If you have to lift your hand to continue tracing that, then there's a break of some sort, and that makes the graph not continuous at x is equal to a. I'll give you a few examples. This one we're very familiar with, y is equal to x squared, very standard parabola opening upward with a vertex at the origin. Now if you were to trace this, You never have to lift your hand to continue tracing it, no matter where, on which part of that parabola you're tracing. So this one right here, there's never any kind of break. This function is continuous for all real x. And it doesn't matter where you go, you can always continue tracing and find a meaningful value of y, regardless of the value of x. We have seen many types of breaks in graphs. For example, this one right here, 1 over x minus 1. All right, so this thing's got a vertical asymptote at x is equal to 1. It's a line that the graph can never cross, and obviously the function is not defined at 1. But away from it, you get these hyperbolas that are really fundamentally no different than the parabola we just looked at. As long as you stay away from that vertical asymptote, everything looks perfectly fine. So that's one example of something that's not continuous. Sorry. You're following the graph here, tracing it. You're going to have to lift your hand when you get close to 1. To continue the tracing here, you got to jump over that somehow. And that's a clear indication that something is not continuous. Here's another example of another break. We saw this function last Friday. It's a rational function. Domain does not include x is equal to 4, so we got a problem at x is equal to 4. But what kind of problem here? If you remember, we factor the top. Turn it into x plus 5 times x minus 4, and downstairs is x minus 4. And as long as we stay away from 4 exactly, these two things will both be the same and non-zero. So we could write this, we could say this is equal to x plus 5, with a very, very important qualification that x is not equal to 4. Okay? You remember what happens at x is equal to 4 to this graph? It's a hole, right? Yeah. Everywhere else, the graph is going to behave like a straight line, x plus 5. So it'll look, well, let's mark 4 right here. If it could get to 4, it looks like it would be 9. Right? And that's that one point we remove from the straight line. Okay, so here's how you can tell without sketching the graph what you got here. A vertical asymptote occurs when the denominator is 0, but the numerator is not. you have something over 0, that means on one side of that line, something is going to infinity or negative infinity. You get a whole here if you have 0 over 0. That's another way to tell what kind of break you got if you don't want to sketch out a graph. Okay, one last kind of break we'll look at is called a jump. And these typically occur when you have piecewise functions. For example, f of x is x plus 3, let's say, if x is less than or equal to 0, or 4 plus x squared if x is greater than 0. These are typically the kind of function that will have jump discontinuities. Okay, so let's see what we get. If we concentrate on the portion left of the y-axis when x is less than or equal to 0, it looks like a straight line, slope of 1, y-intercept of 3. So we get this kind of thing. And this right here would be 3. And the equality belongs to the top here, the left part of that. So the solid dot is going to sit here. The other branch here does not have the equality. And it looks like 4 plus x squared, and that's a parabola opening upward with a vertex at 4. So that branch gets an open circle. And then you have a parabola opening upward with a vertex at 4. Okay, so where the dot is depends on which one includes the equality. If the equality is over here, then the dot will move over here, and that would be an open circle where that number 3 is. And this is called a jump discontinuity. Oops. Discontinuity. Yep, there you go. So a jump, a hole, and an asymptote, these are the typical things we will see. So therefore, if we want the function to be continuous, we want to avoid all three of those things we just saw. To be continuous at x is equal to a, we can't allow the function to have any of those three breaks we just saw. Okay, so let's look at what kind of feature a function has to have for us to avoid having those three things. Looking at this first kind of the asymptote break here, this happens because x is equal to 1 is not in the domain. And that's also the same thing right here. If the number is not in the domain of the function, then we either have an asymptote or a hole, right? So the first thing a function must have for it to be continuous is to be defined at that point. So we say that a function is continuous at x is equal to a if, first thing, we have to avoid the asymptote and the hole, right? So the function has to be defined at x is equal to a. So we can say that f of a is defined. Okay, so once again, this condition here eliminates the vertical asymptote and the open circle. If the function is defined there, you cannot have an asymptote or a hole. So that takes care of that problem. Okay, now let's look at how we can fix the jump. How can we avoid the jump? If you look at the jump here, two different kinds of things appear to be happening at the location you're investigating. So this is indicating that the limit from one side is not equal to the limit from the other side. And that is implying that the limit does not exist. So to avoid this from happening, we have to require the limit to exist at that point. So that's the second requirement we have to have. We require that the limit as x approaches a of whatever function we're looking at to exist. So that takes care of the jump. If the limit exists, then you cannot have a jump. If the function is defined, then you cannot have an asymptote or a hole. However, these two do not guarantee continuity. We have to have one more condition. And the third one requires that the limit, whatever it is equal to, must be equal to the function value at that point. So it's got to be defined, the limit has to exist, and whatever the value it gets has to be equal to the limit. And the third one here is important. Without number 3, you can get into a situation like this one. Let's say this is A. You can have something that has a limit. So that thing clearly has a limit. And something that's defined, but not at that place. Say like right here. Right? This kind of thing is not continuous. If you were to trace that, you have to momentarily jump away from that, put a dot, and then jump back to that curve. So this right here satisfies 1 and 2. It has the function defined, has a value that's defined at A. It does have a limit, but because they're not equal, you have something that's got a discontinuity. So number 3 is to take care of a situation like that. You can look at this as kind of a jump, a very, very small jump. But condition 2 alone does not remove that possibility. Okay, does that make sense? Good. Now if you look at this right here, notice that if we define the function properly, we could move this to patch that hole there and therefore make the function continuous. So I'll write that down here. If we define f of a appropriately, we can patch that hole, right? If I can somehow define this cleverly to fill in that open circle exactly, then I can actually patch it up and make the function continuous. And for this reason, the open circle type of discontinuity is called a removable discontinuity. Think of it as a very mild type of discontinuity. The asymptote is a very serious discontinuity. You can't define the function to fix that. The jump is also a very serious discontinuity. There's no way you can fix it by defining the function to fix that. But the open circle is a mild kind. I can define that dot to sit exactly where that circle is to make the function continuous. So that's why we call it a removable discontinuity. For example, the function that we looked at last time, f of x is equal to x squared plus x minus 20 over x minus 4. Okay, remember this is x plus 5 times x minus 4 over x minus 4. So it's x plus 5 if x is not equal to 4. Straight line with a one dot removed at x is equal to 4. But that's an open circle, right? So we can actually define what the function should be, even though this thing doesn't provide me a value. So we can define f of 4 to be equal to 9. To make this new function continuous. Okay, so we'll define a new function that's based on this one. We will say that the function behaves like this. Whenever x is not equal to 4. So it's a straight line as long as we stay away from x is equal to 4. And then, as soon as I hit 4, I will specify the value to be 9. Right? So the rule of the function is you would follow this whenever x is not equal to 4. But as soon as x is equal to 4, and only at x is equal to 4, you will plug in a 9, no matter what this is doing. Even though it's not defined, we can say that we want it to be 9 at that point. So this is where we patch that hole here. You have this thing which looks like x plus 5, all the way up to that. And then the second branch here says when it's exactly 4, we'll define it to be 9. So that 9 here patches that. Okay, so we fixed the discontinuity by cleverly defining the function to exactly patch up what's missing. And this is the only kind of discontinuity we can fix. You cannot fix asymptote. You cannot fix a jump. It's impossible to define just one point to fix a jump or an asymptote. All right, does that make sense? Questions? Yeah. A horizontal asymptote is not a discontinuity because a function can cross a horizontal asymptote. So a lot of functions don't cross the horizontal asymptote, but many of them do. So it's not a forbidden region, but the vertical is one that you can never cross. So horizontal is perfectly fine. Good question. Other questions? Okay, now let's look at that jump a little bit more carefully. So we're going to jump back to jump. All right, so it's clearly not continuous. But notice that if you just look at the left branch here, we could actually get to exactly x is equal to 0. Whereas from the right, we cannot get there. We could get there from here, but not here. It's kind of like if you only consider one side of the function, then it looks kind of continuous. So that's called one-sided continuity. It's just like one-sided limits that we saw earlier. Just like limits, we can have one-sided continuity. Here's an example. Suppose we have a function, a piecewise function, that's x squared plus 1 for any x that's less than 1, not including 1, but it's equal to a 3 for any x greater than including 1. Okay, so let's check out what's going on here. The right branch is very easy. Very easy. So let's say this is 3. For x is equal to 1 and beyond, it's a constant 3. So it would be a horizontal line like that. And the dot would be included right here because the equality goes with that part. Now the other part looks like a parabola opening upward. If the parabola were allowed to get to 1, it would have a point at 1 plus 1 equal to 2. Let's say right here. Okay. If the parabola were allowed to get there, then that point would be there. But we can't be there, so that's why we have an open circle. We're not allowed to get there. And the rest of that just looks like a regular parabola, like that. Clearly, this is not continuous. Clearly not continuous at x is equal to 1. But we say that it is continuous from the right because we could get to 1 exactly. I'll write down the more precise definition here. But it is continuous from the right because the value of the function at 1 is equal to the limit coming from the right, because f of 1 is equal to the limit x approaches 1 from the right side, superscript plus f of x. Okay, the limit from the right is equal to the function at 1. So we say it is continuous from the right, just like that, like when you have a limit that can fail to exist, but the one-sided limit can exist. Here, it fails to be continuous, but it can be considered continuous from the right because of this condition here. So essentially, you just look at where the equality goes. If I move the equality to the left part, the parabola part, then the location of that dot is going to switch. The solid dot will be here, and that will be an open circle. So if I make this change here, then this function would be continuous from the left. Because the function value at 1 is equal to the limit. I'm running out of space. How did I get myself into this corner? There, fixed it. Okay. So how do you get to the function value? Which side do you have to take? Look at the limit. As you approach, which one can you get there? Here, for this one right here, it's continuous from the right. Right? We could get there from the right, exactly. Here, we can get there from the left, exactly. Now, for something to be continuous, period, then it is automatically continuous from the right and the left. Just like when a limit exists, the right limit and left limit automatically exist and are the same thing. All right, does that make sense? Yeah? Okay. Okay, the good news is that a lot of functions that we deal with often are continuous. I'm sorry? Good? Okay. So where were we? Many functions we often work with are continuous on their domains. And some of these examples are polynomials. Right? Polynomials are always defined, and they're always continuous also. It's very, very nice, convenient function to work with. We know they're automatically continuous. A rational function is automatically continuous whenever it is defined. Like this guy right here, this is a rational function. It is discontinuous when it is not defined at x is equal to 4. But notice that away from that problem spot, it is a perfectly well-behaving function. Right? So rational functions are continuous when they are defined. Root functions are always continuous when they're defined. So are trig functions, exponential functions, and logarithmic. Whenever they're defined, all of these guys are continuous. Polynomial is always defined, but all of these other guys have some kind of domain restriction most of the time. Rational function, when denominator is equal to 0, that's a problem spot. Root function, you can't take the even root of a negative number. Trig, we'll look more at trig functions later on. Don't worry too much about trig functions right now. Exponential, always defined, always continuous. Log has a domain restriction. You cannot take the log of a negative number. But if you stay away from that, log is always continuous. So this means that these three things are satisfied. As long as A is part of the domain, then it is always defined, of course. The limit is always going to exist, and the limit will always be equal to how the function is defined there. So this makes calculating the limit of a continuous function extremely convenient because we know it's defined, we know the limit exists, and we know it is always equal to the definition of the function. So, therefore, if we know that f of x is continuous at x is equal to a, if we know that, because if we know that by knowing it's one of these functions we're looking at, and we're certain that it is continuous, then the limit is automatically equal to whatever the function is equal to at that a. So this makes polynomials extremely convenient when you deal with limits. Just plug in the value and the limit falls out because the polynomial is continuous. And these three things have to happen. Right? So for example, the limit x goes to 3 of x squared minus 5x plus 10 is automatically equal to 3 squared minus 5 times 3 plus 10 equal to 4. And the reason is because x squared minus 5x plus 10 is a polynomial which is continuous for all x. So the limit of the function as x approaches 3 is automatically equal to the function at 3, right? If it's continuous, that has to happen. Same thing here for a log function here. We know log is defined for all positive values of x. 5 is positive, so log of the limit as x approaches 5 of ln of x is automatically ln of 5. Again, because ln of x is continuous if x is greater than 0. And because 5 is greater than 0, the limit is going to exist at exactly where the function is defined. That is just a consequence of continuity. One more quick example here, and then we'll look at something a little bit more complicated. Here, combination of all these things. Here we have a combination of exponential we have a function, right? This part is a trig part, and this right here is a polynomial part. These are things that are continuous whenever they're defined. That is defined for any value of x. Cosine is always defined for any real x. E to the x is defined for any real x again. So all three pieces of this thing are continuous. And if it's continuous, then the limit is exactly equal to what the function would give you at 10 exactly. So that's 5e to the 10 plus cosine of 10 pi plus 500 plus 10, 510, yep. Right? If you know they're continuous, the limit is trivial, really trivial. What's cosine of 10 pi? 1? Are you sure? Yes, it's 1, yep. And once again, we'll look at trig functions in greater details later. For now, don't worry too much about trig functions. Okay, let's do one more example here. A little bit more complicated. Let's say we got a function here defined this way. It's some number c, which we don't know, cx squared plus 2x, if x is less than 2. And some other part, x cubed minus cx, again, c is some number we don't know, if x is greater than or equal to 2. I would like to find the value of c. Such that this function is continuous at 2. Okay, some unknown number c. One part is cx squared plus 2x, which, by the way, is a polynomial. So we know it's going to be continuous whenever it is defined. And it is defined for anything less than 2. The other part is also a polynomial, always continuous for when it's defined, which is greater than or equal to 2. But at 2, we got a split here. We could have a jump. We could have a hole, right? We don't know which one we got here. But we want to find out if we can tweak this number c by choosing the number c appropriately such that they would line up and take away the discontinuity. Okay, so this kind of problem, you just got to remember what it means to be continuous at 2. The 3 requirements have to happen, right? F of 2 has to be defined. The limit at 2 has to exist. And 3, the limit has to not only exist, but has to be equal to what the function is at 2. Check all 3 of these conditions one at a time. If any of these 3 is not satisfied, then the function cannot be made continuous. If all 3 are satisfied, then the function is continuous. Okay? Now the first one is obvious, right? F of 2 is defined. Let's see, is it defined? Yes, when x is equal to 2, it is defined as 2 cubed minus cx. So 1 is satisfied. f of 2 is equal to, you look at where the equality goes. Equality goes with this part, so that's the part you look at. It's 2 cubed minus c times 2, so that's equal to 8 minus 2c. We don't know what c is, but whatever c is, the function is defined at that point at 8 minus 2c. What about 2? How do we make sure 2 is satisfied? How do we make sure that the limit exists here? That's right. We have to get the same number from right and left, right? So for 2 to happen, so 2 limit exists if, a very, very important if, the limit from the right is equal to the limit from the left. If we can guarantee them to be the same, then the limit is going to exist. And once we find the limit, if we can find it, then we'll worry about 3, right? Okay. So let's check out the limit from the left. Coming from the left, this means we're looking at numbers slightly less than 2, which is the top part of that piecewise function. So, and that's a polynomial, like I said earlier. Whenever it is defined, the limit is exactly equal to what it would be. So if you approach 2 from the left, you're simply putting a 2, right? So what do we get? We get 4c plus 4. Similarly, for the limit from the right, we're looking at a value bigger than 2. So we look at the bottom branch. That's a polynomial, always defined. We want it to go to 2. So this will go to 8 minus 2c. Now I can find out c to make these two the same and therefore make the limit exist. And that's pretty easy to do. Okay, limit approaches 2, f of x is going to exist if my limit from the left, 4c plus 4, equal to my limit from the right, 8 minus 2c. So that's easy. That says 6c is equal to 4. So c is equal to 4 over 6, 2 over 3. All right, so that guarantees my limit is going to exist. So therefore, the limit approaches 2 f of x is equal to either of these two. I could take either of these two because I made sure they're equal by forcing this to happen. So this turns out to be 20 over 3. That takes care of the second requirement. The function exists, the limit exists. Now we make sure they're the same. So number 3, f of 2, which we got from the first step, was 8 minus 2c. But we know c we know c, so 8 minus 4 over 3 is 20 over 3. Oh, look, it's equal to the limit. So this means that c is equal to 2 over 3 will make f of x continuous. Okay? All right, that's it. See you Friday. I didn't see any.